it's part of my research agenda that I only half jokingly say is designed to just piss off referees in all fields simultaneously.
But it could be like, the combination of like good things.
Yeah, hopefully we'll see. That's nice of you to say, though. Yeah, it was a fun paper to write, and sort of presenting it in various places. I sort of started to get a feel for how macro people think about this stuff versus micro people think about this stuff. Because I presented in like macro seminars and development seminars, and it's been a fun paper to write.
Yeah. No, I think it's going to help in the long run. But in the short run, maybe it's going to give you trouble with referees, because people have very different views. Like micro people,
that's right.
Persuaded them that this is good enough.
Yeah, I hope. I guess I'll be curious to hear what you say afterwards. But we hope there's sort of like a deeper point in here about like what to do when there's like really important externalities in the aggregate state variable of the economy, and how do we think about RCTs in a context like that. But whether that comes through or not, I guess will depend on how good we are at writing.
No, we have quite a few good applied microeconomists here, so hopefully they're going to give you some useful comments.
Yeah, I'm sure. This paper is still quite new, so there's a lot of the value added of comments is quite high.
So Wyatt has moved to Arizona State.
Just this year. Yeah.
You've moved to Yale, and he moved to Arizona State.
I know, and it was funny because so many people were emailing me, like Gustavo and Natalia and Bertold and everybody. They're just like, is Wyatt good? Should we hire him? I was like, yeah, of course you should hire him. He's terrific. Yeah, he's out there now. He's been sending me a lot of emails about how hot it is and how he's been swimming in his pool every night and all that stuff that Arizona people think about.
Yeah, it's not that bad, right? It's just the summer.
No, I loved it out there. Yeah. I thought it was a great area to live.
Maybe we can wait for like 1 or 2 minutes. People are still coming, I think.
You can see my slides moving and everything. All that.
Yeah. So. Everything is good.
Good.
Yeah. Okay, I think we should get started. So good morning, everyone. Today we are very happy to have Kevin Donovan from Yale University as our guest speaker. Kevin is the rising star in the field of macro development, and today he's going to present from micro to macro in equilibrium diffusion model. Welcome, Kevin.
Awesome. So thanks so much for having me. First of all, it's always a shame when we have to do these things online, but hopefully I'll have a chance to meet most of you in person. I appreciate being called a rising star in the field. That seems to suggest that I'm somehow young, which I feel like is maybe a bit of a stretch at this point. But anyway, so this is joint work with Wyatt Brooks, who's at Arizona State, and Terry Johnson, who's at the University of Virginia. So we're motivated here by this literature in macro growth that thinks about productivity diffusion as either sort of a driver of the development process or something that may, amplify changes in policy in the economy. And just for a very simple idea of what we're talking about here, think about models in which people interact and they get to imitate some of the productivity of the people that they interact with. So if you want, just think about like the Z outside a very simple production function like this. And the key thing in these models is that they're in general equilibrium. And what I want you to sort of focus on here is this idea that, you know, the people who meet today change the distribution of productivities tomorrow, which then impacts who meets tomorrow and prices and all sorts of things like that. And so the model has this equilibrium flavor where the aggregate distribution of productivities is going to play an important role. At the same time, there's this micro development literature that really focuses on detailed studies of specific technology transfers or information transfers. And the basic idea sort of mirrors what goes on in the macro literature in the sense that what you're looking at is you're looking at exogenously shocking the learning opportunity for an agent. But unlike sort of the macro part of this, what you're usually looking at is how does an individual's decision to change productivity or adopt a new technology or their profitability, how do those things change? Right? And so they sort of have the same flavor where people are meeting other people and outcomes are changing. And so what this paper is going to be about is thinking through the relationship between these two sort of parallel tracks of diffusion. And what we'll be thinking about is sort of like, how can we use the micro development results? How can we sort of use this idea of exogenously shocking opportunities for individuals to think about outcomes in sort of the more macro aggregate growth literature? And so that's going to require us to do three things. So the first thing we're going to do in this paper is we're going to derive a theoretical link from the micro results to the macro results. And in particular, what that's going to entail is a procedure by which you can identify macro diffusion parameters using micro RCT evidence. And I'm going to show you that this turns out to be a very powerful procedure in the sense that it applies to a large set of model environments and different diffusion assumptions. So once we have that theoretical link, we're then going to go out and we're going to actually run the RCT in which we're going to randomize meetings between high and low skilled firms in Kenya, which is going to allow us to apply the theory that we set out in the first part of this paper. And then the third part is going to be a quantitative study using those first two steps. So we're going to look at the relationship between the RCT impact that we estimate in the second step and at scale optimal policy that comes out of the general equilibrium model. And that's going to come from us building the estimated diffusion parameters that we come up with into sort of a full GE diffusion model and studying optimal policy. So what are we going to find? So to tell you a little bit about, you know, what I want you to keep in mind going forward for the theory is just to take a step back and think about how we usually identify parameters in a macro model. So in particular, think about these diffusion models, right? So what are you going to do? You're going to make assumptions on the diffusion process. And then you're also going to make another set of assumptions on, say, whether the model is in a stationary equilibrium, how people make occupational choices, how firms enter and exit, distributional assumptions, etc. And the reason you make those second set of assumptions here is because you want to be able to map you want to be able to map parameters to easily observed moments. Right, so what I can see in the data is the aggregate firm exit rate, but then once I combine that with a bunch of assumptions, that's going to tell me something about how fast diffusion is happening. Right? And so, of course, the issue here is to the extent that you've made the wrong assumptions here, you may have biased parameters, which may in fact then bias, you know, what you come up with in terms of policy and things like that. What we're going to show you, or what I'll show you in a few minutes, is that randomization does something that's both sort of common and also very powerful, which is that, like, if you think about what randomization does in just sort of a standard RCT in sort of applied economics, is that it differences out confounds that may affect your estimates without really a lot of structure on the data generating process. What's going to happen here is something very similar, except instead of unobserved confounds, the confounds are going to be model parts of the model that interact with the diffusion process. And then differencing those out from the control group is going to let us sort of identify diffusion parameters without all of those assumptions. And what that's going to mean is that the procedure itself is going to be independent of much of the remaining model structure and is also going to apply to a bunch of different diffusion processes. So for most of this talk, I'll talk about random search, but this equally applies to models with bargaining, deterministic assortative matching, and many other things. And then I'll also show you that it's not like we're going to do anything crazy. So I'm sort of like a very bad econometrician. So this is sort of like exactly what I want to come out of this, which is that I'm not going to require sort of any deep econometrics. All I'm going to need is the average treatment effect, which everybody who's ever done any applied work has tried to figure out. And then also I'm just going to need that and a lagged profit regression that's going to be properly adjusted for diffusion, but I'll talk more about that in a little bit. But what's key here is that the link between the model and the data is very sort of transparent and straightforward. That's all going to sort of come out of the fact that we're using randomization to think about estimating these parameters. Now, on the quantitative side, once we have that theoretical link between the micro and the macro, what we're going to do then is run an RCT in Kenya that implements that theoretical procedure. And what we're going to do is we're going to randomly match low and high profit firms and let them learn from each other. So we have a separate paper where we go through all of the empirics in a lot of detail. I'll highlight some of it along the way here. But the micro outcome that we observe is that if you randomly match low and high profit firms together, the lower profit firm sees a large treatment effect that fades out quite quickly. So we're going to use that and then build those estimates into a general equilibrium model where diffusion happens via random matching and will also allow for some occupational choice. Now, I'm sorry, just a second. If you're familiar with these models, you'll know that the key diffusion externality here is that marginal firms congest the learning process. And so what I mean by that is if people are randomly learning from each other, and if you have a bunch of bad firms in the market, those firms might interact with people and might congest the learning process. When we study optimal policy and trying to correct that externality, we're going to find large gains from policy. Right? So on the micro side, we find large treatment effects that fade out quickly. On the macro side, we find large gains from at-scale optimal policy. What's more interesting here is that those two things do not move together at all. And in fact, what I'll show you at the end is that these micro effects have no direct predictive power for the macro effects that we observe. And in particular, the average treatment effect is going to move negatively with the aggregate gains. What I mean by that is if we had estimated a larger treatment effect in the micro side, the model would then predict smaller aggregate gains. And instead, what turns out to be really important for the aggregate gains is going to be heterogeneity in the treatment effect. And so all of sort of the things we generally think about when we run RCTs, which is, this idea that you could sort of run the RCT as a test of, taking policy to scale, those things are not going to be true here. And it's going to be because of the role played by the aggregate state of the economy. And I'll be much more specific about that. But what you should take away right now is that the micro and the macro effects tend to move in opposite directions. Okay, so if there's no other, when I stop for just a second.
Can I ask a question?
Yeah,
sorry.
Yeah, please.
So it's been like 5 pages, so I can ask a question actually.
No, yeah, of course.
So I think it's actually a general question. So you've mentioned that for micro studies, usually they focus on a specific technology, like tractors or like electricity or something like that. But in macro, when we talk about the technology or like diffusion, we think about like a combination of like all the technology, right? So I guess it's actually about the external validity of the study. So how do you think about this? Like how to bridge this like a micro and the macro studies?
Yeah, that's a great question. So can I hold off on that for one slide?
Sure.
I'm going to show you exactly what we do.
Okay.
And in particular, what we're going to argue for is that sort of the macro way seems to make more sense if what you care about is sort of this broad-based diffusion of knowledge.
Right.
I mean, studying one particular technology is nice because it allows you to, say, track diffusion through a network, because there's only sort of one margin you need to keep track of, which is like, do I plant improved seeds, right? Or something like that. But of course, as you point out, we know that that's only a small part of what we would generally think of as productivity in sort of a macro sense.
Sure. Yeah.
And we're going to argue for that macro way of viewing the world. And in part, this first part right here, I'm going to make assumptions that's going to let me sort of map that into things that I can observe in reality. That's going to be sort of key for us. And then we're going to defend it when we go to the RCT. And I'll in fact show you that, you know, when you match two people together, it's not like all of them are getting together and they're all figuring out the same thing. It's that they're figuring out like wildly different things across people, and they're talking about different things, which all seems to suggest like if what you care about is diffusion, you know, sort of thinking about it in a bit of a broader sense than a single piece of technology is more important. But okay. I'll point out exactly where this comes up along the way. And in fact, it's going to come up on the next slide.
Okay. Cool.
Yeah, that's a great question. Okay, so are there any other questions? I'll keep going. Great. Okay, so feel free to jump in and stop me whenever. So the way I'm going to lay this out for the rest of the talk, I'm going to go, the first part of this will be the theory. I'm going to not lay out a full model. Instead, I'm just going to lay out the assumptions that we need to make the estimates work. And I'll sort of talk through those assumptions. Then we'll go on to identification, sort of walk through some of the identification results. And then we'll turn to the empirics where we actually run the RCT and the quantitative implications of building that into a general equilibrium model. Okay, so what I want to focus in on here is the class of models in which this identification procedure holds. So I'm going to make 3 assumptions about the world. If you forget what those assumptions are, they're going to be down here on the bottom of the slide for the rest of the talk, so you don't have to remember them, because God knows I would forget all of them. But we're going to live in a world, think about a world where it's infinite horizon, and there's a measure 1 of firms who have productivity Z. Each period, every firm is going to get hit with 2 shocks. The first shock is what we'll call an imitation shock. So if you see a Z hat, anything with a hat is coming from somewhere else. If you get hit with an imitation shock to Z hat, you're going to adopt it if it's profitable to adopt it. And I'll be specific about what exactly profitable means in a second. And then there's also going to be some random innovation component. Right, so there's just going to be some epsilon. Each period, you'll get some random innovation to your productivity that doesn't depend on this imitation shock. Okay, so that's the world I'm going to live in. Then I have to make 3 assumptions. Assumption 1 is, what is the thing that gets transmitted when people meet? And I'm going to get at that, I'm going to assume that profit is proportional to productivity. What that lets me do is that when I observe variation in profit in the data, I'm going to be able to interpret that as variation in productivity. So this gets to Zikon's point about how do we sort of think about productivity here. We're going to think about it essentially as profitability. Right? And so this is sort of more of a macro take on what productivity is than, say, sort of like a more micro-specific piece of information or technology. So that's assumption 1. Assumption 2 is we need some way to figure out, we need to parameterize how productivity evolves. And we're going to assume that it takes this form right here. So forget about this max operator for a second. If you just cover that up, this is just an AR1 process, right? So you can take, maybe I should write this in logs, but if you take logs of this, you can see it very easily. This is just an AR1. But then what we're adding to that is we're saying, all right, well, if you get hit with an imitation shock and it's better than your current productivity, you get to increase your productivity by the ratio of that raised to some power beta. Right, so this beta, this elasticity beta is going to turn out to be very important. It's going to be one of the parameters we estimate. Right, so this is an AR1 process sort of modified by the fact that there's this diffusion imitation opportunity coming to you each period. And then finally, we need some idea of sort of who meets with who. And so we're going to assume that these imitation shocks, the Z hat shocks, are going to be drawn from a distribution M hat, which can depend on your own productivity, and then also some parameter theta, where theta is going to order these distributions via first-order stochastic dominance, in a first-order stochastic dominance sense. I'll talk more about this in just a second. So I'll talk more about this as we go through. But what this assumption is buying us is that it's limiting the dynamics in the search and matching decision. And I'll be very explicit about this. And in fact, I'll show you where the results fail if you don't assume this. Okay, so let me just spend another second on this M hat distribution, just to sort of give you a sense of what we're thinking about here. So think about a world with random matching. There exists some equilibrium distribution of productivity in the economy. Let's just call that M. And then what we're going to assume is that everyone draws from what we'll call a distorted version of that distribution. So M is the distribution of productivity in the economy. And then the shocks, the imitation shocks, are drawn from M raised to this 1 over 1 minus theta. So if theta equals 0, these two distributions are equal. This is just uniform random matching. But as theta changes, so sorry, I'll show you this graphically. Here's the equilibrium productivity distribution. If theta equals 0, they're the same thing. What happens as theta gets higher? It starts pushing the distribution of draws away from the distribution of productivity, right? So the higher theta is, if it's low, they're equal. And as it gets higher, it sort of pushes that distribution away. So this is a way to sort of parameterize where the draws come from relative to the equilibrium productivity distribution in the economy. So like I said, I'm going to sort of work under a random matching. If you look at the paper, excuse me. If you look at the paper, we have a big appendix that goes through how to interpret this for a number of different processes. But just to give you some sense, there are a number of different things that fall under this same assumption. So for example, theta could be the distribution of a draw, or sorry, the probability of receiving a draw. It could be the max over theta different draws. Or it turns out theta can be a measure of noise in the diffusion process. It could measure the bargaining power of one party. Or in fact, you can go all the way to deterministic assignment models where theta then becomes the gains from complementarity between two people. All of these fall under our procedure, and it just sort of, the only thing that changes is how you interpret this parameter theta. Okay, so like I said, those are the three economies. And now what are we trying to do here? So we're going to think about this class of models where profits are proportional to productivity, and the diffusion process is governed by this law of motion here, and imitation draws are drawn from distributions like this. We're going to think about rho, beta, and theta as our three key diffusion parameters. And then in fact, I'll show you that they are really the three key parameters. Our goal is to identify those parameters without adding all of the additional model structure that you might need in sort of a more standard macro model. model, if you will. And the way we're going to do that is we're going to use this as what I'll call sort of like a top-down use of randomized control trials. So instead of using randomized control trials to build up from the micro level, we're going to posit the macro, and then we're going to use this to just hit, to sort of like hit the key parameters that we need to estimate. Okay. And if there are no more questions, then I'll get right into the identification. Okay. So I gave you my 3 assumptions on how the world works. Now I'm going to propose hypothetical variation in the data generating process. So in this world, imagine now that we observe a population of agents with some productivity distribution, and we observe them for 2 consecutive periods. Then we're going to take those agents and we're going to randomly divide them into a treatment group and a control group. And what's the treatment going to be? The treatment is we're going to find some other set of people who are not in this population of agents that we're drawing control and treatment from. And we're going to make sure that they're really high productivity. So think about a world in which we grab a bunch of random people, but then we also have this other group of very high productivity agents. What the treatment is going to do is it's going to guarantee the person in the treatment group a match with somebody from this high productivity set. So the treatment is guaranteeing you a match from way in the right tail of the productivity distribution. And in particular, what we're going to assume is that the person that you match with is always more productive than you. That turns out not to be super important, but it's going to like dramatically simplify the math. And so we're just going to assume it for the sake of simplicity. Okay, so you get guaranteed a good match, but then the exact person that you're matched with is a random assignment, right? So again, just to sort of highlight this, we take a group of people, we split them into control and treatment, and then we have this other group of really productive people, and then we're going to randomly match people in the treatment group to one person in the treatment group to one person in this high productivity set, and we're just going to do that on a one-to-one basis. The key thing to take away from this is that there's 2 randomizations here. The first randomization is into the treatment and control groups. And then the second randomization is that the exact match within the treatment, those are randomly assigned to. So this lets us interpret the average treatment effect causally. What this second randomization is going to do is let us interpret variation within the treatment group as causal variation. Right? And that's going to be really critical for us. Okay.
Yeah. Can I ask you a question?
Yeah. Please, yeah.
Maybe you're going to explain later, but I'm going to ask anyway. So how are you going to determine who's like a high productivity person? How are you going to determine whether a person is of high productivity?
Yeah, so we're essentially going to look at their profits.
Profits, okay.
Yeah, right. So that's going to follow from this first assumption that we make.
Yeah. That
profit is essentially productivity.
But you're going to look at like the average profits or just like profit in reality, the profit could be high because the person is highly productive, or could be like the person is like well connected, or the person is like just lucky.
Yes. Yeah, so that's a great question. So 2 things. Well-connected and lucky are sort of different things to think about in this context.
Yeah.
If that's what's going on, when we go to the estimates, we would not see any relationship between how good your match is and what your outcomes are. Right? If it's all just sort of like luck, or like it's only connected people who are really profitable and they can't diffuse that connectedness, if you will, right? Then when we go to the data, we shouldn't expect to see sort of a relationship. Like if I meet with you and you're really smart, if you're really good at diffusing productivity to me, and you have a lot of productivity to diffuse, then I should gain a lot from that meeting, right? If it's true sort of like pure diffusion.
Right. Yeah.
If it's just that you're connected and that's why you're so profitable,
right,
and we meet, then I shouldn't see any gains out of that, right? So that's something that's going to come out of the estimation. But in sort of a general sense, you're right that one of the ways where sorry, I'm going to answer a slightly broader question because it's useful to point out, which is that one of the ways in which this proportionality assumption fails is if there are idiosyncratic distortions, right? And however you want to generate them is up to you. But like any sort of Shea and clean out type thing is not going to allow this to hold true.
Sure.
And so we have an appendix in the paper where it shows sort of like, if that's the case, everything I'm going to tell you is a lower bound.
I see.
And so I'm going to show you some pretty big numbers at the end.
Yeah.
So if you think it's sort of more connectedness, that type of thing, then just inflate all of the numbers that I show you.
Oh, I see. So that's like, okay.
Hey, Kevin.
Yeah.
Hey, this is Zhiwang from Fudan. Can I clarify one thing about the matched firm? So you just mentioned that you're going to match firms with a high productivity firm, right?
Mm-hmm.
Are those firms from the same industry or they are doing different
good
business?
Question. Yeah. So this is all random conditional on industry. That's right. Yep. Yeah.
Okay.
That's not critical here, but certainly when we take it to the data, that's going to be important.
Okay.
Yeah.
So another thing is, I know there is a strand of literature studying peer effects from like classrooms or dorms. So are those the environment also relevant here?
That's a good question. So that's a great question.
Mm-hmm.
So my general feeling is yes. The reason I'm hesitating is because you have to define an outcome.
Mm-hmm.
And so here, the outcome is productivity. And then because we can't observe productivity directly, we have to map it to something that we can observe directly, which is profit.
Mm-hmm.
So that would be my only concern. In general, yes, they would fall exactly under this type of framework.
Mm-hmm.
But if you had an outcome in mind that wasn't directly observable and you were concerned about, say, making an assumption about proportionality to something that was observable, that's where you could sort of get into trouble, if that makes sense.
Okay, in that case, for example, in classrooms, people usually use test scores as an outcome. Right? But I think the difference is also like the inputs. There are also, for example, for firms, their labor, their capital, and those decisions are also affected by, for example, the other peers or the other firms. Yep. So I think they're more complicated than the peer literature.
Perhaps, it's you might be right. So I'll say sort of like two things about that. One is that just as clarification, certainly like this assumption does not assume that there are no other inputs. It just assumes that the production function is such that its profits are proportional to productivity. And in fact, when we write down the full model, there's going to be labor and such things in there. In terms of the peer effects, I don't know. I guess my prior was that if you're thinking about, say, a classroom setting, there's like the school building and there's the teachers and there's sort of like the quality of do you have computers or books and things like that?
But I guess maybe those things are given.
I guess that's a great point. Yeah, so I guess the difference is that like kids don't control those in the way that firms do. That's right. Yeah, no, that's right. So maybe it is in fact simpler. And in fact, if you're looking at, say, test scores, and test scores are directly observable, and you want to write down a diffusion law of motion like this, that's even better, because then you don't even need this assumption. Right? If I could observe Z, I wouldn't need this proportionality assumption, because I would just observe Z directly. And so I think maybe you're right. Maybe there is something here. Maybe there's like a broader sort of set of models that one could use something like this for. Yeah, I think that's probably right. That's a great point.
Okay, thank you very much.
Okay, cool. Okay, so here's my big claim. And then, I'll sort of walk through some of the simple parts of the identification, and we'll get into, maybe the more interesting empirics and quantitative stuff. So my claim is that this type of variation is enough to identify these three parameters without any additional structure on how the model works. And again, that's beta, which is this diffusion elasticity, this rho, which is sort of like the persistence of productivity, and then this theta term here that governs the distribution of draws. Okay, so the way I'm going to lay this out is I'm first going to identify beta and rho only using data from treatment firms. I'm going to forget about the control group altogether. Then I'll come back and use the control firms to identify this theta term. So how do we get beta and rho? So start from this law of motion of diffusion. So I've just taken this diffusion law of motion down here and just written it in logs. Now I'm just going to take a bunch of the assumptions I've made, and I'll remind you of what they are, of course, and just walk through how we get from this equation to something that you can estimate from data. All right, so the first thing is, within the treatment group, the person you get matched with is always more productive than you by assumption, right? So we just made this assumption. What's nice about that is that notice we've got this max operator here, and max operators are always a pain to work with when you're trying to run regressions. And so that assumption gets rid of the max operator. So now we're getting somewhere. Now we make this assumption that profits are proportional to productivity. That's going to be really nice here, because I'm going to be able to take all these Z's and just turn them into pi's. So when I implement that assumption, I've got something that looks like this, and the only thing that differs here is this constant. Okay. So now, if you look at this equation, this is just like a panel regression, right? So this is just saying my profits tomorrow depend on the decay of my profits today, plus the relative difference between my match's profit and my profit. And that's just a panel regression. Now, I guess it's actually a cross-sectional. Yeah, no, I guess it's a panel regression. Now, there's two ways to interpret this. So this is just like, I apologize if I'm just going through econometrics 101, but I sort of think it's useful to think through these various parameters in this way. So you could look at this regression, and you could focus on beta here. What is beta? What beta is telling you is how much does a match impact your future profit conditional on your profit today, right? So this is like saying, take my profit today as given, how much do I get from meeting with somebody who's really productive? A second way to read this is to say, all right, well, what I want to do is I want to estimate the persistence of profit over time. But of course, in diffusion models, that's a little bit complicated, right? So let me give you an example. Imagine I observe somebody with high profit today and high profit tomorrow. One possibility is that the world is just really persistent, right? Profits are just really persistent. Another possibility is that profits aren't persistent, but the person who had high profit today met with a really good match, and therefore their profits stayed high despite the lack of persistence. So what that means is that you need to adjust that persistence regression, which is exactly what this does. So a different way to read this same regression is to say, this is a regression of the decay in profits over time, but controlling for how good your match is. Right? Those are two different ways to read the same regression, but because of the randomization within the treatment, in fact, this regression is telling you both of those things simultaneously. And the estimates beta hat and rho hat that you get out of this regression are in fact the unbiased estimates of the true underlying structural parameters beta and rho. Right. So this is what I mean when I said at the beginning that, you know, the econometrics here are pretty basic, and that this is a regression that, you know, you could have your undergraduates do on a homework problem. But because of sort of the way we built these assumptions into the model and sort of the link between the RCT and the theory, it turns out this is all you need. Now, it turns out that, oh, sorry, yeah, go ahead.
Can I ask a question? So here, I guess, when you implement this, you just pick out the really highly profitable companies or firms, right? So by assumption, this Z hat is going to be higher than Z in the treatment group, I guess.
Yes,
what would happen if it's lower than Z? I mean,
sure. Here we go. There's my next bullet.
Okay.
So yeah, that assumption turns out not to be required.
Okay.
All you need to guarantee that this works is that the treatment group has to be drawing their draws from a different distribution than the control group.
Right. Yeah.
So if there's some overlap in those distributions between, like, if there's somebody who has Z higher than the Z hat, that's okay, as long as the distributions are different.
Right.
Now, the problem with that, for the sake of a talk, is that, if you'll excuse me 1 second, I'm just going to go back a couple slides.
Okay. Yeah.
If you don't make this assumption,
yeah,
you have the max operator in here.
Right.
And then running OLS on max operators is sort of a mess.
Yeah.
And so it turns out then the same exact intuition that I just gave you goes through, but it's then a two-step procedure. And when you have a two-step procedure like this, now all of a sudden, like, there are existence problems and you have to be careful about uniqueness. And so there's a big proof in the appendix that goes through how to solve this without this assumption. But it's not like, there's no economics in it, unfortunately. All the economics are in this one. And then there's just like, you have to be careful about fixed point theorems and things like that to sort of like push the results through without that assumption. But it turns out you can do it. It's the exact same idea. It's just a little, to exactly your point. You're just, instead of talking about individuals being different, instead of talking about like everybody's match being better than them, what you end up talking about is the distribution of matches being better than the control distribution.
I see. Yeah. Sorry, I have actually another question here. So it's about the magnitude of beta. So in reality, I guess it's not like if two persons meet, then they instantly learn from each other. It's another important dimension is like the how long they've like meeting with each other and like how often they meet. Right. Yeah. So I guess that matters, right? It's just not just like from this functional form, it seems like it's just like it's not wrong because that's everybody just doing that, right? You meet, then you. I guess that's the assumption in the Lucas paper as well, right? If you meet, then you learn from the other person. But in reality, I guess the duration and all the other dimensions matter as well.
Yeah, it's a great point. So we've been thinking about this a little bit, and in fact, I won't show it to you today, but if you look at our other paper where we go through the empirics of the RCT, one of the things that comes out is that people who meet longer have a higher treatment effect. Now, of course, there's like selection and all sorts of issues that you run into trying to interpret those results. But to a first approximation, it does seem like there's something to that. I don't have a great answer for you in the sense that part of how I think about those types of issues in this model is that you meet with somebody and you sort of get the immediate effect. And then you could keep meeting with them, but like their profits are changing because they're going through the same diffusion process, and there's decay in the profits and there's mean reversion. And so I suspect there's like a mapping between the two of them, but but I should be careful sticking too strong to that stance because I haven't quite solved it yet. That's a good point. But yeah, maybe we should just do it. It's a relatively straightforward extension to just say like,
because I mean, there's another big literature on the like the learning curve or things like that, right?
Sure. Yeah.
I mean, if knowledge can be transmitted like instantaneously, then a lot of the issues will be solved. We could just have internet. We don't have like a university, right?
Yeah, but I mean, so there's a different constraint here, right? Like, this is like Paul Romer's big critique of this stuff, which is like, why doesn't the smart person just write a book and then it's over, right? The constraint here is that you can't meet with everyone simultaneously.
Yeah, sure.
So there's like a congestion in sort of like a search sense, right? So that's sort of the constraint that stops this from like, even if everything is instantaneous, because not everyone can meet with everyone in the same instant, there's still sort of like a time dimension and a role for the planner here.
Yeah. Okay, I see.
Yeah. Okay, cool. Okay, so I don't need the z-hat assumption. It also turns out, depending on who you ask, this proportionality assumption is not like strictly required. What's required is that you can identify Z from the control group. So I have to be able to identify Z from panel data in the control group.
Sorry, Tim. There's a question.
Yeah. Sure.
So my colleague Duncan asked, so will productivity measure error due to distortion or markup drive the estimated beta and row bias, even in RCT?
Great question. Yeah. So I hope I have that. I'm going to do something very risky, which is I am going to go to my appendix slides and hope that they're in there. So let me just, excuse me for 1 second as I really skip ahead. Don't look at any of these results. Keep the suspense alive here. Let's see. Here we go. All right, so let me just show you this right now, because this will be sort of like useful to think about. So the answer is yes, markups, idiosyncratic distortions, it'll bias beta and rho. It will not bias theta. And so I'll explain to you why that's true. But the key thing to think about here is that now imagine at birth, everybody draws a productivity shifter that can't be diffused, right? So this is the idiosyncratic distortion. Now what you have is profits are proportional not to productivity, Z, but to this term. So I've written this as a Cobb-Douglas, which sort of allows me to get the proportionality. So this is sort of a problem, right? This does not satisfy our assumption that profits have to be proportional to productivity. And if you sort of work through the math, this is a disgusting slide, but here's what we had here's the true technical equation. This is the structural diffusion. But if you write down this proportionality, what you end up with is like a clear bias term here. Right? So this is the equation I wrote. This is the equation I showed you in the main text. But now there's all this noise and other stuff floating around in the error term. And that's exactly the bias that you just hypothesized, and it's indeed correct. So you can actually write this down. You take some very basic probability limits on these things. And what you end up with here is that you get a downward bias of this thing I'm calling eta, which is just rho minus beta. And you get a downward bias in beta, right? So this is the true variance of the match productivities. And then that thing gets downward biased by the variance in these idiosyncratic distortions. Right? And so what you end up with here is something like this, which is that if you give me the value of the distortions, then I can readjust these things to sort of get rid of the bias, right? But I don't know what this thing is, so you sort of have to do the regressions for a given value of the distortion, right? So that's a very long-winded answer to say you're absolutely right. These things, markups, idiosyncratic distortions are going to downward bias my estimates. And so what I'll show you when we go to the quantitative results is that we're going to find pretty big effects from this already. And if you think that there are these idiosyncratic distortions that are also operating in the background, everything I'm telling you is a lower bound on how large the gains from policy are. So that's sort of the key thing to keep in mind. But yeah, absolutely. That's a great point. And here's sort of the formalization of that point. All of this stuff shows up in the error terms, all these idiosyncratic distortions new. All right, so let me just go backwards. Okay, great. Any other questions? Okay, terrific. So now we have beta and rho, and the last thing we need to do is we need to estimate theta. The thing about estimating theta, and we're going to use the average treatment effect to do this. The problem is that we cannot observe how the control group is matching, right? I, as the researcher, control the treatment draws just by the fact that it's in an RCT. But you got to remember here, the control group is also going through this underlying diffusion process in the background. And we can't observe what they're doing. So think about it like this. Oh, sorry, this is CDF. I guess these are PDFs. But, yeah, take the derivative of M hat, I guess. These are PDFs, sorry. Right, so just think about this. This is the distribution of control draws if theta equals 0. And then what does the treatment do? Remember, the treatment guarantees a good draw. So the distribution of draws for the treatment group is going to look something like this. Now, if theta starts to increase, remember what that parameter is doing. It's shifting the distribution of draws to be better and better. So if theta is high, we're going to get a control group. The control is going to draw from a distribution that looks like this. If theta is low, it's going to look like this. What does this tell us? Well, it tells us that if we observe a small average treatment effect, that must be coming through the fact that the control group is already pretty good at finding high quality matches. Right? So if they're bad at finding good matches, and we then guarantee the treatment group a good match, then we're going to observe a huge treatment effect. If the control group is already very good at finding the best people, and then we guarantee treatment groups a match from a good person, it's just not going to do very much, right? Because the control group is already essentially doing what the treatment does. And so without observing control group matches, the average treatment effect is going to let us infer what's happening with the control group and sort of how good they are at finding matches. So this is the intuition of that idea. You can do the math. The math is not particularly beautiful or anything like that. This is the average treatment effect. Once we replace all the z's with pi's, and then we already estimated beta and rho, we can observe these distributions from the data, which means the only thing left in this equation is theta. Theta is the only unknown once we estimate beta and rho. Okay? But then we made this assumption, we made this first order stochastic dominance assumption, which means that there's a unique value of theta that solves this problem. Right? This is just the average treatment effect. Everything here is already solved. First order stochastic dominance gives us that there's a unique value of theta that solves it. Okay. So just to sort of rehash this, step one is identifying beta and rho, so the parameters of the diffusion law of motion using only data from the treatment group. which relies on variation in match quality within the treatment. And then the second step is identifying theta as a function of those values of beta and rho. And that just comes right from the average treatment effect. And so that's it. That's all the theory. That's sort of what we want to do, and how now we want to use that to think about, how big are the gains from diffusion? How should we think about the relationship between these things? Oh, sorry, I'm just checking the time. Yeah, I'll mention a few things. I promised I'd show you where the results failed, so let me show you those. So I'll just mention here, we estimated beta rho in this equation right here. It turns out this is actually a little bit broader. What our procedure actually allows for is it lets you estimate rho and then a non-parametric function f of any characteristic sets between the individual and the individual they get matched with. Right, so the reason for this is just because everything's randomized, right? And so if I think, for example, that productivity tomorrow not only depends on the profit gap between two firms, but also say the age gap, well, age is randomized. And so I can put, I could estimate, say, age-specific betas without any problem or any real change to the procedure I wrote down. If you sort of take that intuition to its limit, that gives you this non-parametric function here. Excuse me. So we're not going to go any farther than this. We're just going to focus on this case with a single beta. The reason is twofold. One is because the literature tends to do this as well, but also there's practical issues of power that come into play when you're trying to estimate functions like this. But I just wanted to highlight it to point out that there's a much broader type of model you could solve using these types of methods, which was brought up earlier about on the question about, say, like maybe you could do this in schools or something like that, where you might think a broader set of characteristics are going to become important for understanding the diffusion of whatever outcome you're interested in. Okay, so there's a subtle restriction on theta that I want to highlight, which is we make this assumption that m hat takes this form down at the bottom here. When does that fail? It fails whenever there are dynamics in the matching process. So what I mean by that is, imagine you have to pay a cost today that affects your ability to match in the future. Why would that be a problem for us? Well, if I make a decision on whether to pay the cost today, that decision depends on what I view the economy looking like tomorrow, right? Because that's when that cost is going to pay off. And so almost immediately, you lose the independence of this estimation procedure on the rest of the model, right? Because what does the agent need to forecast what the economy is going to look like tomorrow? She needs all of the structure and sort of like what's happening with entry and exit and all sorts of the underlying economics. The same thing is true, for example, if the benefits of the match depend on an input that has a market price for the same reason, right? Like imagine I'm deciding whether to meet with somebody today or meet with somebody tomorrow. If that decision depends on an input that has a market price, one thing I might do is I might wait until tomorrow when that price is lower. Well, what determines whether the price is higher or lower depends on what the equilibrium looks like, whether we're on a balanced growth path, all sorts of things like that. And so you can't sort of generically estimate theta without the remaining structure. Now, I'll just mention a couple things that are useful here. One is that even if you write down a more complicated model, you still need a lot less structure in this format than you would otherwise. So for example, in both of the examples I just gave you, if you assume that the world is stationary, neither of these things are a problem, right? The market price today is the market price tomorrow, or the cost today is the cost tomorrow. If you have things like that, then you can still use the same procedure. The other thing is that violations of this m hat assumption only affect theta. right? So if you want, you can always sort of choose the value of theta ex ante, and you can still estimate beta in rho, right? So there's some trade-offs here in terms of model complexity versus estimating one of these parameters that, you know, you would have to take into account if you wanted to do something a bit more complicated. But just to be upfront about sort of like where the model sort of has some trouble, this is it right here. Okay, so that's the end of the theory. And now I want to get into some of the empirics and talk about the RCT and how we work through some of these things. All right, so we're going to conduct an RCT in Nairobi, and we're going to do so among young female business owners. Not because we think there's something particularly gendered about diffusion, but because it turns out they make up most of the business owners. And so this was just a goal of trying to limit heterogeneity within the sample. The treatment is a random match to a high profit business owner from outside our study population. So this is exactly sort of the hypothetical variation I gave you earlier. And you'll notice here, here's the first randomization into the treatment group. And then the second randomization comes from the random match within the treatment. So both of our orthogonality conditions are going to be satisfied here. What is it? How do we actually implement this? So we go to this productive person and we say to him, hey, would you be willing to help a young person learn about business? They were only asked to meet once during November 2014. So we ran this a few years ago, like pre-COVID, I guess is the key distinction. And we didn't give them any specific topics or meeting lengths or any cost. There was no cost to not meeting. So the goal here was to try and stay as close to the theoretical counterpart as possible, where we weren't, you know, as Zikan mentioned at the beginning, we weren't trying to sort of target a particular type of change or a particular piece of information. We just sort of wanted, you know, sort of what the model would tell you, which is that there's a lot of things going on and sort of what they choose to talk about should be up to them. Then we went to the treatment firms and we literally just gave them the phone number of the person that they were matched with. Whether they ever met or not was up to them. It turns out 100% of them actually met, so this was not an issue. But there was no other sort of like prep on, you know, convincing people to meet or like priming them in some sort of way. So the goal was just to sort of get two people in contact with each other who hadn't met before and see what comes out of it. So what do we find in the reduced form? If you look at the treatment effect, it's around 14%, a 14% increase in profit, just the average treatment effect. Now we track people for 6 quarters. And what I'll show you a little bit later is that the gains are concentrated in the first 2 quarters. By 6 quarters, there's no effect left. Now, actually, this result was what got us started thinking about this paper originally, because what people told us was, well, if there's no gains left by 6 quarters, then how could you possibly think that diffusion is happening? And in fact, what I'll show you is that I'll show you that the gains from diffusion are large. And also the model is going to be able to replicate this type of time series. And so I'll show you that towards the end. Now, the other thing that I haven't really talked about, but shows up sort of implicitly in the way I've defined things, is that if you're the more productive person entered into one of these matches, this assumption down here suggests you shouldn't see anything. You shouldn't see any change. Those people, of course, aren't randomized in the RCT, but given the way we do the selection procedure, you can run a regression discontinuity on those people, and we find no changes in profit or any sort of business practices that you might associate with profitability. And so this max operator does, in fact, seem to be the right assumption. If you're interested in more of the reduced form, obviously I'm happy to talk more about it. We have a separate paper that goes through a lot of this in more detail and you know, highlights a lot of different features of this.
I have a question.
Yeah.
So those matched persons, so they've met like only once or something? So they've like only met once in November or like a couple of times?
No, so the program itself was meet once.
Yeah.
Whether they kept meeting or not,
yeah,
we obviously we didn't stop anyone from meeting. Okay. We just didn't tell them it was part of the program. Okay. So a lot of them did keep meeting for a longer period of time, but that was not like, we went to them and said, hey, I just want you to meet this person once and talk about business. And then some of them formed relationships and etc.
Okay, so you don't have information on that, on like the follow-ups?
No. In fact, we do.
Okay.
We do.
Yeah.
So we know how long they met, all sorts of things, which is why to your earlier sort of related question, this is something we could do. We could sort of like look, like I said, you have to be a little bit careful about sort of like the selection into meeting and things like that. Exactly. But in, net of those types of things, we could sort of study that in the context of the model. If you sort of allow people multiple period meetings, for sure.
Given this, like you were asking them to like help the young people, I guess it's not surprising that there's no impact on the senior people, because I mean that's what you ask, right? You teach the young people, so it's just like the one way. So there's only the effect from the more productive people to the younger person, I guess.
I was actually, so I wasn't thinking of it so much as positive. I was actually thinking about it more as like, I was worried that, right, so what does this model tell you? This model, like this functional form right here, tells you that meetings generate surplus.
Yeah, sure.
I wasn't so much worried about the more productive person seeing a positive effect. I actually was worried that they would see a negative effect.
Yeah.
Right? Like they have to take some time out to work with this person, that kind of, these are high marginal product of labor people, and we're taking their time away. So that was what I was worried about. I was worried that what we were going to see is just a transfer from the more productive to the less productive, with no surplus actually being created.
Yeah.
And that worried us because this model says very clearly that these are surplus creating matches. Yeah.
I mean, if you think about like the more general form of like learning or spillovers, so in your setting, I guess it's also true in, I'm not sure about the Lucas paper, I guess, if somebody is better than you, then you learn, right? But you could think about like more general forms of learning that like people have different ideas. Like some ideas can be good, some ideas can be bad, but when you exchange ideas, you have two, like that sort of things.
Yeah. So I completely agree. It's a great point. So let me make sort of two small comments about this.
Okay.
One way to interpret theta is how much noise there is in the diffusion process.
Yeah.
Right. So you and I meet, and then theta sort of governs, like, you can sort of think about it as like, when we actually meet, do you actually give me like the good stuff or the bad stuff?
Yeah.
And so you can sort of see how that's related, right? So like I've been describing theta as like how much better the matches are than the equilibrium productivity distribution. But you could also think about a scenario where like, oh, maybe they just match with whoever, but some of the matches end up being really bad just because like there's so much noise in the process. That's sort of the same thing, right? It's like noise is just saying that the draws are drawn from something other than the productivity distribution.
Sure. Yeah.
Right. And so that we can handle through theta. This idea of sort of like maybe some ideas are bad. Maybe you meet with somebody who's actually really good in one dimension, but that dimension isn't sort of the same thing that you need. Those things are all sort of built in here. And that's just sort of like a different way to interpret what theta is. In fact, you wouldn't have to change anything. You just literally, it would be the exact same thing, the exact same model, and just theta is a different interpretation.
Sure.
There was something else. Shoot, no, sorry. I went on such a long-winded answer to your first part that I forgot what I was going to say to the second part. Did I answer your question?
Yeah.
Okay,
that's
cool.
Fine. I mean, if you remember later, then you can.
What were you asking? I said I had two things to say, and I failed on the second one.
That's fine. Yeah.
Shoot. All right. Sorry. Yeah. If I remember it all, I'll yeah.
Yeah.
Yeah. Sorry. Okay. So yeah. So this is sort of like what we find in the reduced form. Now, Zikan, this gets back to your earlier point. This is sort of why we like. This is why we like thinking about this in sort of the way the macro literature would, because if you look at what people are talking about, they're not talking about one thing. These are a bunch of the different things that people are talking about when they meet. You know, there's attracting customers, there's sort of keeping better records, how to lower the cost of inputs, how to price products. You know, should they be increasing the varieties of things that they sell, all sorts of stuff like that. So there's no sort of one thing that dominates these discussions,
right?
Which is sort of exactly what we wanted to be true. Now, you might look at this and you might say, oh, maybe it's just heterogeneity across firms, but it's not. It's actually within firms. So if you look at the number of topics discussed, there are 10 topics here. This is the CDF of the number of topics each match discusses. And what you can see here is that, you know, like 40% of them are discussing more than half of these topics within the match. And 20% of them are discussing all 10 of these things. So it's like, it's not the case that they're all getting together and everybody's just saying, no, you know, what you need to do is you need to buy from this guy over here. What they're doing is they're saying like, boy, your businesses are pretty unproductive. You should probably be thinking about like how to attract more customers, but you should also be thinking about like how you price your products and where to source lower goods and things like that. So there just seem to be like a lot of different pieces that go into this Z, which we sort of like because it's, you know, our intervention is very light touch relative to the rest of the micro literature, where we're sort of not taking a stand ex ante on what constrains these businesses. We're letting the matches figure them out themselves. And they can choose as many things as they want to talk about. And that seems to be exactly what's coming through here. Okay, so we've got about 20 minutes. All right, so now because of the way we've set this up, like I said, the econometrics are very simple. So what we're going to do here is we're going to estimate everything only off the first two quarters. So the pre-period and then the first post-period. And then we're going to use the remaining quarters to see if we can match the fade out of the RCT. So we're going to sort of take that as a measure of sort of like model quality, if you will. If you estimate this equation, like I said, this is just a panel regression from the treatment group. You get rho equals 0.59 and beta equals 0.54. These numbers don't really mean anything until you take them to the model, but you know they're significant, you know, as you would hope. When you estimate theta, you get something that looks like 43%. And so this is log theta just on our treatment indicator. This is the average treatment effect in the first quarter after the treatment. And so from there, we're just going to go to the macro side and see what we can see. All right, so if there aren't any questions, I'll sort of put on my macroeconomist hat and go down that route. Okay, great. So what we want to do now is we want to think about what are the aggregate gains from policy. And, you know, you just can't do that without a model, right? Because the aggregate gains from policy sort of depend on this fixed point problem that requires an aggregate state variable. And so we need to sort of build this into an aggregate model. So here's the model we're going to write down. The value of having productivity Z, given a distribution of productivity in the economy M, is going to be equal to this. So let's just walk through this piece by piece. There's going to be occupational choice. Excuse me. You can choose to be a firm, in which case you'll earn profit pi, or you can be a worker at those firms and earn a wage W. The profit function is going to be Cobb-Douglas. So there's going to be labor because you got to hire the workers. But you'll note that the Cobb-Douglas assumption gives us the fact that profits are going to be proportional to productivity as we've assumed throughout. There's going to be exogenous exit. So a fraction delta of people are just going to exit the market every period. That's just to make sure that the economy stays stationary. And then you're going to wake up tomorrow and you'll have some expectation over what your productivity will be tomorrow, given the evolution of the aggregate state. So what's going to determine that expectation? It's going to be the meetings, right? So your productivity is going to follow the same law of motion we've had for the whole talk. And then I'm going to make this assumption here that M hat follows this thing, this distribution right here. Now this might look a little bit funky, but it's exactly the same thing that I showed you earlier. What is this saying? Well, the first thing to note here is that this functional form, this sort of risk neutrality here, is going to generate a cutoff value. So if your profit is high enough, you're going to be an entrepreneur. If you're below some cutoff, you're going to go work for those entrepreneurs. That cutoff is the lower bar. So what this thing is saying is that people in the economy only learn from active firms, right? So if the Z is bigger than this cutoff, you're going to learn from those firms. And then that's just adjusted by this parameter theta again. And so it turns out that's the whole model. Nothing super complicated, but just basically reformulating what we had before. And I should mention this is in general equilibrium. So like this wage right here will clear the market. This law of motion has to be consistent with how people are making decisions, etc. Now, the thing to keep in mind as we go forward here, thinking about aggregate effects, is just sort of this thing right here. People only learn from active firms. And so what the planner is going to want to do is the planner is going to want to sort of push this cutoff up into the right tail to kick out the least productive firms so that people only learn from better and better people, right? That's going to be sort of what the planner is working on. And I'll formalize that planner's problem in just a second, but just keep that in mind. That's sort of the key thing here. There's an externality because some marginal people decide to become firms. And if they become firms, people learn from them, and that sort of congests learning from the good people. All right. So I won't bore you with the rest of this, but we calibrate the rest of the model in sort of a very standard way to match a bunch of moments from our data that we've collected in Kenya. Including the variance of profits, the variance of new firms, age distributions of firm owners. And the model, it's not a particularly detailed or deep calibration, but the model doesn't have any issue matching any of the moments that we target. This is just the sum of squared errors across all of the moments we're targeting. Okay. So, if there are no other questions, let me stop for a second before I dive into the results. Okay, great. So we're going to try and ask 3 questions. We'll see if I get to all 3 of them in 12 minutes or so. First thing we want to do is just study, is the diffusion externality in the model large, right? And so we're going to do that by comparing the laissez-faire equilibrium with the efficient equilibrium. And then we'll study how important the parameters we estimated are for generating that result. And then we'll go into trying comparing those results to the estimated RCT effects and things like that. So let's just start with the first part. How big is the diffusion externality? What we're going to do here, as I mentioned, the key inefficiency in the model is that marginal firms decrease the ability to learn from good firms, right? And so what the planner wants to do is the planner wants to kick those firms out so that nobody learns from them anymore. The way they're going to do that is they're going to subsidize wages, right? So you can do this through any number of policy levers. In a simple model like this, it turns out to be not super important. But so we're going to allow them to subsidize wages. What does subsidized wages do? It takes people who are right around that cutoff who want to be firms and pays them a higher wage so that now they leave and become workers instead. So that's going to be the planner's margin for being able to push people around and change the learning externality. If you do that, what you end up with, just focus on this first number here, average income goes up by over 300%. There's a big change in terms of income by allowing the planner to sort of optimally manage diffusion, right? So this suggests that diffusion is actually quite important in this economy at the parameters we estimate. Now, I should note, this doesn't have to be true, right? A logical outcome of this, had we estimated different numbers, would be that this value is 0, right? So there's nothing that sort of forces this to be 300%. What's going on? Well, as I just mentioned, notice what the efficient economy has. It has almost everyone working. What does that mean in terms of learning? It means that everybody in the economy is learning from the top 1% of productivity, right? So that's how the model is sort of able to generate more income. It's because there's so much learning going on from this. Sort of as you might expect, because more and more people are working, average entrepreneurial productivity goes up by about 900%. That also has the benefit of increasing the wage by 48%. Right? So all of this is just to say, it does seem like there's a big diffusion externality in the model at the parameters we estimate. What we want to, sorry.
Just to clarify, so the average income increased by like more than 300%, but the wage only increases by like 48%.
Right.
So that's the average income of each person or each firm.
This is the average income of everyone in the economy.
Everyone.
Yep.
Okay.
Yeah. So what's happening here? Is that the distribution of productivity is also changing, right? The aggregate state is changing.
Yeah.
And so profits are going way up too.
Yeah.
Right. So that's why I know I agree. This number looks small, but it turns out once you do the accounting, it's just that the key, I guess, for those of you that are familiar with these models, the key here is like how much weight you get in the right tail of the productivity distribution.
Yeah.
And so that's what's going on here. You're getting just like the planner's able to just like fatten the tail of the productivity distribution. And these things have such big tails because of sort of like all of the diffusion that keeps happening that you can get these like really big changes in productivity from the model.
Okay, so I guess one implication is that, there are too many self-employed people in the developing countries.
Indeed. That's right. And this isn't even taking into account sort of like, you might not want those people operating firms because they should be working for people with like larger spans of control. This is saying like, even without that, just the diffusion itself suggests people.
Yeah,
exactly.
You want to learn from the best.
Exactly. Right.
Okay.
Yeah. In fact, that's exactly what the planner's doing. The planner's saying, well, in baseline, only 30% of people want to work, but that's not at all what we want in an optimal economy or an efficient economy. Sorry. Great. Okay, so let me skip this. This is just the CDF of productivity. You can see it gets pushed out quite a bit by the planner relative to the baseline. Okay, so how much do our parameters matter? So I'm going to recalibrate the full model, assuming beta equals 0.25. That's about like a little more than half of the baseline value. The gains from optimal policy I just showed you were 345%. If I recalibrate the model with beta equals 0.25, that drops to 156%. Still big, but quite a bit different, right? So we're going to take this as evidence that getting these diffusion parameters right actually matters quite a bit. The gains from policy declined by about 55%. If I just fix beta, if I keep the baseline calibration, but only lower beta, the gains from optimal policy are 184%. The thing to note here is that if you compare these two rows, almost all of that aggregate drop is coming from changing beta. 85% of the difference between the two models is only coming from changing beta. The rest of the parameters, the calibration, turn out to play a much smaller role. Altogether, the rest of that stuff captures 15%. Beta is getting 85% of it. So beta is really the key parameter here. The thing to remember about beta is that beta is estimated in a way that has no relationship to the average treatment effect of the RCT. That's all coming from sort of the heterogeneity or the co-movement with your match's productivity. So that's what I want to sort of think about next. How much does sort of our standard RCT average treatment effects actually tell us about these gains from policy? And this result right here is the first indication that that's probably that the RCT results are not going to be sort of directly useful. So in the last 5 minutes, let me explain to you exactly what I mean. So what we're going to do is I'm going to recompute all of those optimal gains from policy under counterfactual RCT estimates. So if I estimated something different from the RCT, how do the equilibrium gains from diffusion change in response to those estimates? So what I've got here is these are the gains from optimal policy and general equilibrium on the y-axis. And then here is the average treatment effect that we estimate from the RCT. Our results, our baseline results are somewhere in here. But you'll notice here that this is declining. Right? So the larger the average treatment effect you would have estimated in this RCT, the smaller the gains from policy at scale. Why is that? Well, the thing to remember here is that theta is controlling the ease of finding a good match. Right? Theta is saying like the higher theta is, the better agents are at finding good matches. At the micro level, what that means is that the smaller theta is, so the harder it is for control firms to find a good match, the larger the average treatment effect is going to be. But at the same time, if theta is controlling the ease of finding a good match and the economy is having a really hard time finding those good matches, the planner has a much more difficult job of trying to direct matches to the right tail. And so these two effects are moving in exactly the opposite direction. And you get this negative relationship between what happens at the micro level and what happens at the macro level. Because the key thing to remember here is that the RCT is explicitly trying to difference from a control group, where the equilibrium gains are trying to contaminate the control group via good matches. So it turns out to move in opposite directions. If you look at the heterogeneity in the treatment, so what would happen if we estimated beta equal to 0.2, 0.4, 0.6, etc., what you get is that it's increasing for most of this. Don't worry about this decline here. If you're interested in that, there's a section in the appendix about it. It's just sort of about the shape of various things. It's not, well, I haven't found much use for it. So don't worry about that for now. If you're interested, there's a big discussion about it in the appendix of the paper. Here what you see is that this thing is increasing. So the more heterogeneity in the treatment via this parameter beta, the larger the gains from policy. Why is that? Well, beta controls the gains from a good match, and that thing is estimated completely independent of the average treatment effect. So it's not using sort of these usual RCT moments. But if beta controls the gains from a good match, that makes the planner's job quite a bit easier. Right? What do I mean by that? Well, the planner's using the fact that if they can direct people to good matches, those people gain a lot from the good matches. That increases productivity tomorrow, and then that sort of result just sort of builds on itself and builds on itself through the equilibrium. And so the higher this beta is, the easier the planner's job is. So the planner's looking for not looking, but, so to speak. The planner's job is easier and the gains from policy are larger if beta is high and if theta is high. But a high theta means low average treatment effect. High beta means there's just a lot of variation within the treatment effect. Those are the two things you want, not necessarily looking for a high average treatment effect, as you might sort of expect, or as is usually done when looking at RCTs. So to put that slightly differently, imagine you're a policymaker, and imagine you're trying to look and say like, oh, where is diffusion policy going to have the biggest impact? I know, I'll run some RCTs where I randomly match people together and see how large the gains are. If you were to think about deploying optimal at-scale equilibrium policy based on RCT evidence, you would go in exactly the wrong direction. And in fact, you would minimize the potential gains from policy by just sort of naively using the RCT estimates as a stand-in for the gains from policy at scale. And what you need instead is you need an ability to link those RCT estimates to the underlying structural parameters. The key thing here is that the general equilibrium externality, this diffusion externality, it's all operating through the aggregate state of the economy. Now, if you've ever thought about sort of like how the design of RCTs, you know, what you're trying to do in an RCT is explicitly hold that fixed. You're explicitly trying to hold the aggregate state of the economy fixed to eliminate control group contamination. And what we're saying is that the macro all comes from that. That thing you're trying to hold fixed, that's where all of the aggregate gains are coming from. And so once you sort of take those two things apart, these parameters can play all sorts of different roles in various contexts. So I'm just about out of time. Let me skip this last part about the dynamics. The model can match the treatment dynamics, and there's all sorts of interesting results. But let me just conclude in the last second here. So this is a paper trying to link together micro evidence and macro diffusion models. And so a big part of this is trying to draw a link between these two things, both in theory and in practice. I'll just mention in the last second here, one thing that didn't come up, but also seems to come up quite a bit when I present this. This is not a paper that tells you what the right model of diffusion is, right? I'm not telling you sort of what the diffusion process is. I'm sort of positing that it takes a particular functional form, albeit a broad functional form, and then running the model that way. And so I think sort of the next step of all of this is starting to use these types of results and using these RCTs in this sort of like what I called a top-down method to study those types of questions. What is the right model of diffusion? Can we start distinguishing across these various models? So I'll stop there. Thank you very much for your comments. They were super useful.
Thanks, Kevin. So any questions?
Yeah. Kevin?
Yeah.
And can I ask a question about the marginal firms?
Sure.
So if we are in the environment of a classroom, so what are those marginal firms? Are they bottom students or they're middle students?
Well, that's a good question. Boy, sorry. I'm also trying to find my slides. There we go. All right, there we go. Found them. Good. Yeah. I don't know. So this is sort of what I was talking about on the on the conclusion there.
Mm-hmm.
Who is marginal depends on what diffusion process you have in mind.
Mm-hmm.
Right. So like the reason why there are marginal firms here is because I've structured the model in such a way that like there's like a cutoff where you only learn from firms to the right. Mm-hmm. And so I think like it would sort of depend on how you view these two terms in a classroom setting. Mm-hmm. Does that make sense? So I'm not entirely sure that there's a clear answer. If you think that people are learning from the worst students in the class, like if you think that there's some spillovers from those people, like, you know, you're really smart and I'm the worst kid in the class, and you're worried that we might bump into each other, then they would be sort of the people that the planner would want to take out. Mm-hmm. or if you think that somehow like the class is more sort of like people are in little groups where maybe I'm so dumb that, you know, I never talk to the smart kids like you. And so there's just sort of no matching between us. Then you'd want to think about sort of the marginal person within the group of people you're learning from. Right. And so like what form that process takes depends on sort of what you view as the reasonable sort of model of learning.
The diffusion is a positive spillover from high performing students to others. And if we assume that this spillover effect is getting smaller as the knowledge gap widens between the high students and the others. So those bottom students, the marginal ones.
Sorry, say that once more. I didn't quite follow the last part.
So now the spillover is from the top student to the others. And so if we assume that the spillover effect is decreasing as the knowledge gap, for example, the test score gap between the top and the other student widens. So are the marginal students the bottom ones?
Oh, that's a great question. That's a great question. I don't know. So here it's the opposite. And what I mean by that is the larger the gap, the larger the gains that come from those two people meeting. If you assume it goes the other way, ooh, I don't know. That's like saying like, that's a really good question. I don't know. I mean, I don't think it's too far off from what I have written down here, but I haven't solved that. And so it's not obvious to me how to think about.
I just wrote a paper about within classroom learning, and we saw that when bottom students sit next to a top student, we did see they get like higher score in later on tests, but I also see this gain becomes smaller as their knowledge gap, the test score gap gets bigger. So it's trying to figure out what we should do in order to, for example, improve the overall academic performance within a classroom.
I mean, I think so. I think the answer in like a broad sense is this law of motion then is perhaps not a good representation of what you're finding. Like it sounds like you have a lot more information on sort of what the functional form of this thing should take. Or I guess maybe a different way to say it is, if you'll permit me to go back a few slides, is that you actually have some more information about what should go into this function f. And so then once you start estimating those functional forms a little bit differently, you can get different types of policies that should arise relative to sort of the simple one that we have where there's a cutoff and like it's obvious who's marginal and who's not. These more complicated functional forms will give you more complicated optimal policy rules. Which maybe that's sort of the right way to think about this is like even before sort of applying a procedure like this, you can actually go quite a bit farther than us if you have a bunch of these characteristics and you can estimate this semi-parametric function instead of this sort of like fully parametric function.
Okay. Can I clarify another question? So in your environment, are the marginal firms the middle ones? So those.
So they. I mean, so I should be a little bit careful about my language here. So I'll say this in a couple I'll give you sort of like a slightly more technical explanation and then sort of like the more intuitive one. In search models, there's a condition called the Hosio's condition. Yeah, I don't know. These are things I was learning about as I was doing this, which sort of equate the marginal gains from kicking somebody out to the like marginal cost of losing that person's, in this case, output. There is no Hosio's condition here. So it doesn't matter where this cutoff is, there's always an inefficiency. So like the model is always inefficient. So there's no sense in which like I would say, oh, it's the middle firms or it's the low firms. That's just sort of a function of the parameterization of the model where that cutoff lands. Here, I can tell you where it comes from. So you can sort of see it here, right? So like line everybody up on a productivity line. This is saying the 31 at baseline, the top 69% of productivity become firms, and the bottom 31 become workers. So like the cutoff is somewhere around the 30th percent. And then the planner is saying, okay, everybody between 31 and 99 is in fact marginal from the view of the planner. Right? So it's like this huge group of people, or firms, I should say, to be specific, that the planner is saying like, all right, we don't want you in the economy anymore. We want you to be workers where nobody's learning from you and you're just sort of like, you're not using any of your human capital, you're just sort of using your raw labor to help other people with higher human capital. So yeah, so I'm not entirely sure whether they're the middle or they're the, I mean, yeah, technically they're, the marginal people, I guess, are between the 31 and 99th percent.
I see. Okay, thank you.
Okay, so my colleague Dunker had another question in the chat room. I'm going to just read it to you. Okay.
Sure.
So I noticed the identification of theta is based on that it governs the aggregate productivity differences between the treatment and the control. Due to randomization, aggregate productivity can be calculated without the model structure. Now, if RCT was implemented just for one period, the productivity of firms could evolve over time. Then, with model structure with entry and exit be essential to aggregate productivity?
That's a good question. No, I don't think so. I mean, you would, well, I should be careful. Yeah, yes, it would be, in the sense that you would need to take into account if firms are closing, right? So why would a firm close in this model? A firm would close because they get like a really bad sort of exogenous shock to their productivity, and then they would close. So yeah, so I mean, we ran this, let's see, we ran this for 1.5 years. We didn't have any differential closures between control and treatment, but if we did, yeah, you would want to take that into account somehow. You would want to, I guess it would sort of depend what you did with productivity. Well, no, it's profit. No, it's profit. So you would give them a 0. You would just say like your profit is 0, right? And so you would take those zeros into account here as sort of like the profitability of the firm. Yeah. Yeah, that's a good point. So indeed, you would want to take seriously the idea that firms are entering and exiting.
Any other questions? Okay, then actually I'm gonna ask a question. So, so as you know, there's like a big literature, both like empirically and theoretically, which studies the effects of like barriers to firm entry on aggregate productivity. Then from the perspective of your results, it's like, what's going to be the effect of those barriers in your model?
That's a good question. That's a good question.
My hunch is that
oh, sorry, go ahead.
Yeah, it could have like positive effects, right? I mean, because you push all those people out of the business world and make them into like workers. Yeah.
Well, but it's also going to have negative effects in that the planner is going to have a much harder time sorting people based on productivity.
Yeah, sure.
Right? That's like what the planner's goal is, to sort on productivity. Yeah. And my suspicion is that inability is going to swamp sort of like what I think is what you're saying. Correct me if I'm wrong. Okay. This idea that like it might hold people out of starting a firm.
Yeah.
But that's only useful if it like holds the unproductive people out of starting a firm.
Yeah.
If it just holds like a random distribution or a random like a uniform what is it? I guess it's a uniform distribution over the productivity distribution or whatever. You know what I mean?
Okay. Yeah.
If it's that case, then I think that's going to make the planner's job harder, and that's going to lower the gains from diffusion. It's an interesting question, though. I mean, it seems like both of those effects are going to be there. So it's this just by intuition that one would dominate, but I don't have a theory that tells me that that's true or anything.
Sure. Because I mean, you have an interesting new mechanism, right? It's not in the old literature actually. Yeah.
Yeah, that's right. There's Diego Rastusha and some others have some work now looking at sort of like distortions in the context of diffusion models.
I see.
But I don't think they're so much worried about the entry-exit margin, so to speak. They're sort of just thinking about like, if it's harder for you to invest in your own productivity in a model of diffusion, then naturally like diffusion is harder because people's productivity is lower because they can't invest, which is sort of like, I don't want to say obvious, but like, it's sort of obvious.
Yeah. Okay. Any other questions? Okay, then thanks, Kevin. It's a really nice paper and a really nice talk. I guess it's already pretty late on your side. Thanks a lot. So unfortunately, this is just like a virtual visit to our school. So hopefully, when this craze is over, you can like visit us like personally and physically.
Yeah, that would be great. That would be terrific. Thanks so much for all your comments. And thanks for, I'm sure like with the time difference, it's tough for everyone. So thanks for being there this morning. And I'm looking forward to talking to a few of you tomorrow.
Yeah. Okay.
Cool. Thank you.
All right. Have a good morning.
Good night.
See ya.
Good night.